Okay, hello. We are going to continue um, with the section. So the section we're on is section 8.1, and what I want to do is um, kind of quickly go through and review what we were trying to do in class, which is with this example, we're trying to do this example, but to use the method of rejection regions. Okay, so we've done quite a bit, and now I'm just going to kind of briefly go over all of it again. And so, of course, if you don't want to watch or don't need to rehash this example, then, feel free to skip right on through or speed up the pace. And hopefully you can see everything that I'm writing. So we'll be good with that. And also, I'm going to kind of go back and forth. Actually, I'm not going to erase the requirements for the test, but we'll do. So this is kind of where we'll start. So just as a recap, we are doing a 2-sample z-test for the difference between means, and sigma 1 and sigma 2 are known. Okay, so we had you can pause and read the information here. We're looking at credit card debts between California and Illinois. Okay, so since we have 2 samples, it's not going to be the first 3 options, right? 2 samples for the difference of means. We're not doing proportions, we're doing difference of means. So it's the mean amount of credit card debt. And we've got independent samples, and sigma 1 and sigma 2 are known, so that is our choice. So we highlight this one, this option. And the requirements for the test, we wrote these yesterday and it's still valid. Sigma 1 and sigma 2 are known. The samples are independent. The samples are random. The populations are both normally distributed, or the sample sizes are both greater than or equal to 30. Okay, so now we can go ahead and let's redo this part about determining the null and alternative hypotheses. Okay, so it's the same method that we used in dealing with Chapter 7, which is a 1-sample hypothesis test. So we look at the claim. The claim is that there is a difference in the mean credit card debts of households in California and Illinois. So our claim is that there is a difference in mean credit card debt in California and Illinois. Okay. So to translate this into a mathematical statement, what we want to do is we want to say mu1 is not equal to mu2. And so here we can indicate that mu1 corresponds to the average household debt equals the average credit card debt in California, and mu2 is the average credit card debt in Illinois. We write the complement of this statement, which is that mu1 is equal to mu2. The top one is our claim. And so we figure out which is our null hypothesis. It's the statement with the equal sign. And the other statement has to be our alternative hypothesis. Okay, so we can go ahead and write that over here. So in our null and alternative hypothesis, null hypothesis is that mu1 is equal to mu2, and the alternative hypothesis, mu1 is not equal to mu2, and the claim is the alternative hypothesis. The distribution to use for the test is a z-distribution because sigma 1 and sigma 2 are given, are known. Okay, now what is the test statistic? The test statistic is always, when we're doing a hypothesis test for the mean, for the difference of means, x1 bar minus x2 bar. So in the case here, x1 bar is 47.77 and x2 bar is 48.66. So we'll have 47.77 minus 48.66, which is equal to, I believe it is equal to negative 89. I think that's what we did. Negative 89. Now, what is our standardized test statistic? Okay, so to calculate our standardized test statistic, which we actually need for doing the rejection method, we'll use the following formula. So here we are doing our standardized.
It's 9:15.
Test statistic. Okay, the formula is z equals x1 bar minus x2 bar minus the quantity mu1 minus mu2 divided by sigma x1 bar minus x2 bar. And now here, just to explain what these symbols mean, this is the hypothesized difference, mean difference. Remember, when we're performing our hypothesis test, we always assume this is equal to 0. Okay. It is possible to do hypothesis tests for 2 samples and not have the assumption that the difference is equal to 0. So you could have the assumption that the difference is equal to 10 or whatever you want. But for the problems that we'll be doing in this book, we're making the assumption that this difference is equal to 0. Now, this first quantity here is our test statistic, right? So we actually calculated it. And so this is going to be equal to negative 89, right? Because that was the first thing we did was the test statistic. And then this last quantity, which is a standard deviation, we have a formula for it. So the formula is that sigma x1 bar minus x2 bar is equal to sigma 1 squared over n1 plus sigma 2 squared over n2, and we need the square root of all that. Okay, so if we go ahead and fill this in, let's compute this. We're going to get this is equal to the square root. Now sigma 1 squared is 1045 squared. N1 is 250. So let's see here, just so you can check. Sigma 1 squared is 1045, and N1 is 250. Sigma 2 is 1350, and N2 is 250. So that's kind of how I'm doing this. Okay, plus 1350 squared divided by 250. So this is going to be equal to, let's see here, 1045 squared over 250 is 4368.1, and 1350 squared divided by 250 is 7290. So we'll have the square root of those. When we add 4,368.1 to 7,290, we will get 11,658.1. And when we take the square root, we will get 107.973. And we can say that that is approximately, well, yeah, we can leave it at that, 107.973. You want to be careful in general. This is just a general statement for statistics, especially when you're doing your online homework. You want to be very careful about rounding too much in the beginning while you're doing your calculations. So here I'm going to leave it at 107.973. So now back to our formula for z. So we'll have z is equal to negative 89 minus 0 divided by 107.973, right? Because we've got the x1 bar minus x2 bar, which we said is negative 89. And then we have the mu1 minus mu2, which we said we always assume is 0. And then lastly, we've got our standard error, standard deviation, which is 107.973. Okay, so now this is equal to negative 89 divided by 107.973, and this is approximately negative 0.8241. So this is going to be our test statistic, our standardized test statistic. Z equals negative 0.8241. And now remember, you can also get this, you can also do this quickly or more quickly by using your calculator. So the output on your calculator, the output when you do a 2-sample z-test, includes the standardized test statistic. Now, we're not going to do the p-value because remember, we are using the method of rejection region. So instead, what we need to do is we need to find the rejection region. Okay, so let's go over here. So we're going to find the rejection region. Now, the rejection region is going to be based on two things. It's going to be based on alpha and whether your test is left-tailed or right-tailed or two-tailed. So the first thing is that alpha is equal to, in this problem, alpha is equal to 0.05. So alpha is 5%. Alpha is 5%. Okay, 0.05 is alpha. And what type of test are we doing? Are we doing a left-tailed, right-tailed, two-tailed? I'd look here at my alternative hypothesis. And because the structure of the alternative hypothesis is not equals, that means we're going to have a two-tailed hypothesis test. Okay, so since we're having two-tailed and our alpha is equal to 0.05, essentially our picture, it's not a good picture, but here's what the picture is going to, let me try to do a better job. Okay, so here's our picture. Our picture is, we've got a t-distribution, and the area for our two tails needs to add up. The area of the two tails needs to add up to be 0.05. So this area is going to be equal to 0.025, and the area in the right tail is going to be the same thing, 0.025, because t-distributions are symmetric. Our critical points are going to be whatever these t-values are, or these z-scores. So these are our critical values, TC. And so in this case, to find TC, you can do your inverse T. This is if you have a TI-84. And first you put in the area, and then you put in your degrees of freedom. Right, so this is the formula to find TC. So for the area, we need the area in the cumulative area. Cumulative, which is the area to the left or the area below. So for us, our cumulative area is going to be 0.025. And we need the degrees of freedom. So what are the degrees of freedom? How do we find the degrees of freedom? Well, usually the degrees of freedom is typically it's n minus 1. But we've got two values for n. So let's see here. So looking here, I think we should have a formula for the degrees of freedom. What am I missing? Oh, I'm going crazy. We don't have a t distribution. Remember, we have a z distribution. Because sigma is known, we have a z distribution. So that's why I wasn't able to find a formula for degrees of freedom, because we won't need the degrees of freedom because we are dealing with a z distribution. So let me go ahead and correct that. If you noticed my mistake, good job, right? And if you didn't, make sure that you listen to it again to understand why we don't have degrees of freedom. Right? It's because we don't have a t distribution, we have a z distribution. So instead of finding inverse t, you find inverse norm, right? Because we have a normal distribution. And for normal distribution, there's only one, the standard normal distribution. So inverse norm, our area, cumulative area is still 0.025. The mean is 0, standard deviation is 1. And so when we do that, let me go ahead. So instead of TC, we're finding ZC. This will be ZC minus ZC and ZC. So to find ZC, this is what we do on the calculator. This is for both TI-83, TI-85, and TI-89, all three of those. And this ends up being negative 1.96. So our critical values are going to be negative 1.96 and positive 1.96. So our critical values plus and minus 1.96. And our rejection region is going to be anything that's more extreme than plus 1.96 and anything that's more extreme than minus 1.96. So here in the picture, we would have our rejection region as any values down here and any scores, right? Any scores less than negative 1.96 and any scores greater than 1.96. So the way we write that is negative infinity to negative 1.96 union 1.96 to infinity. And the last thing we're going to do is we're going to look and see our test statistic is negative. This is our test statistic, negative 0.8241. And if we put it on our little scale here, negative 0.821, now we said this is going to be negative, our left critical value is negative 1.96, and our positive critical value is 1.96. Our test statistic is negative, like negative 0.8, so that's a little less than halfway, negative 0.824. So it is not in the rejection region. So we say our test statistic, standardized test statistic, is not in the rejection region. So we fail to reject H naught. Okay, and the last step, which is our interpretation of our decision. And here's what's going on. So we failed to reject H naught, and our claim What is our claim? Our claim is HA. So since we failed to reject H0 and our claim is HA, there's not enough evidence to support the claim. So let's put in here at the, what is our alpha? Our alpha was 5%. So at the 5% significance level, there is not enough evidence to support the claim that, what is the claim? The claim is there's a difference in mean credit card debts in California versus Illinois. So that California and Illinois have different mean credit card debt amounts. Okay. So there we go. And so you can see here when we have our rejection region and doing the rejection using
It's
the
9:30.
method of rejection region, the first step is to find your critical points, right? So the first step is to find your critical points. And then in order to do that, you have to know alpha and you have to know that your test is two-tailed. Once you find your critical points, since you know your test is two-tailed, you can determine your rejection region. Then you take your standardized test statistic and see if it is in the rejection region. If it's in the rejection region, then you reject H0. In this case, our standardized test statistic was not in the rejection region, so we failed to reject H0. Okay. And so we've got this stuff here. Same information. Let's look at our second example. And for this example, we're not going to use the method of rejection regions. We're going to use the method of p-values. Okay. So take a moment to read the problem. You can pause it. Pause the video. Okay. So our setup is going to be very similar. We are talking about the average daily cost of meals and lodging for vacationing in Texas versus Virginia. So our claim is going to be, let's see here. Give me 1 second. Okay, so our claim is that the average daily cost in Texas is less than the average daily cost in Virginia. So to translate this into a mathematical statement, we'll just write mu1 is less than mu2. We take the complement, mu1 is greater than or equal to mu2. And the complement is our null hypothesis. The claim is the alternative hypothesis. So we can go ahead and fill that in. Our null hypothesis is mu1 is greater than or equal to mu2. Our alternative hypothesis is that mu1 is less than mu2. And the claim is the alternative hypothesis. Okay, the requirements are the same. Sigma 1 and sigma 2 are known. Sigma 1 and sigma 2 are known. We need random samples. We need independent samples. And lastly, we need for the population to be both populations to be normally distributed, or both sample sizes are greater than or equal to 30. Okay. And the test that we're going to use is going to be a test with two samples for the difference between means with independent samples and sigma 1 and sigma 2 known. Okay. So here we can go ahead and highlight that information. So it is a hypothesis test for two samples because our two samples are from Texas and Virginia, and it is for the mean because here we're given this information about the average. Average is another way of saying mean. Let's see here. Sigma is known. Sigma 1 is known. Sigma 2 is known. Okay. We're supposed to assume that both populations are normally distributed, so we satisfy that requirement. So notice that even though our sample sizes aren't greater than or equal to 30, it's okay because we are assuming, or we know, that both populations are normally distributed. So we've covered that sigma 1 and sigma 2 are known. The samples are random. The samples are independent. And do we have the random samples? Let's see here. Here we go. Random survey of vacationers in each state. So that's how we get, that's how we know that all of our requirements for the test are verified. Okay, so let's do the next step, which is state the claim to use for the distribution. We're going to use the, state the distribution to use. We're going to use the Z distribution because sigma 1 and sigma 2 are known. What is the test statistic? Because we're doing a hypothesis test for the difference between means, our test statistic is going to be x1 bar minus x2 bar, which is equal to 234 minus 240. 234 minus 240, which is equal to negative 6. Okay, now what is the standardized test statistic? Again, the standardized test statistic is actually, the standardized test statistic is something that is automatically spit out from your calculator when you do your two sample z-test. And the standardized test statistic should be z equals negative 0.912. Okay, the p-value is going to be p equals 0.1808. So in your calculator, you've done your two sample z-test. You've input x1 bar, x2 bar, n1, n2, sigma 1, sigma 2, and the last thing you need to put in is your is what type of test are you doing. Okay, so you look at your alternative hypothesis and you're going to select the option with less than. So there should be some screen with something like mu1 equal to, not equal to mu2, less than mu2, greater than mu2. And so you want to select the less than option. Okay, and so now what we'll spit out is part of what the output will be your standardized test statistic. Okay, another part will be your p-value. So in one or two sentences, complete sentences, let's explain what the p-value means. What it means is the probability of selecting two samples, right? One in California and the other in Virginia, or one in Texas and the other in Virginia, and taking the surveying two, right? Two samples, taking the average of the daily costs that the people spent, and getting a difference in the means, their sample means, which is as extreme or more extreme than -6, than -$6 is, what is the probability of selecting two samples? That probability is about 0.1808, which is roughly 18.1%. And this is, of course, assuming that there is no difference. No difference in the costs in Texas versus Virginia, right? So, of course, if there's no difference, even if there is no difference in the mean costs in Texas and Virginia, just because you pick two samples doesn't mean that they're going to have the same sample means, right? Because, it's random. So you could pick a sample where the mean is higher for one than the other, right? Even if the population means are the same. So what we're saying is, assuming that there's no difference, what's the likelihood of selecting two samples and their sample means being as extreme or more extreme than -$6? Well, that's like an 18% probability. So of course, for our decision, since alpha is equal to, what is alpha equal to? Alpha is equal to 1%. So alpha is equal to 0.01. And our decision is going to be to fail to reject H naught. Why? Because P is greater than or equal to alpha, or P is greater than alpha. And the interpretation of the decision is at the 1% significance level. Since we are failing to reject H naught and HA is our claim, there's not enough evidence. So there's insufficient evidence to support the claim. And what was the claim? The claim was that the average daily costs for vacationers in Texas is less than the average daily cost in Virginia. And Texas is less than that in Virginia. Okay. And then the last thing, which I see we kind of forgot to do here, is we're going to need to sketch our standardized sampling distribution. So we're going to sketch the Z distribution. We know that our standardized test statistic is -0.912. Because this is the standard normal distribution, the center is 0 and the inflection points are 1 and -1. So the -0.912 is going to be just this side here, right? So -0.912. Okay. And then, let's see if I can clean this up even a little bit more. So I put in the inflection points for just so I can know. But now my shading is going to come from, there we go. So I'm essentially going to be shading, right? And we know it goes on forever, but this area is equal to our p-value, which is 0.1808. So so here's the area that we're shading. I only shaded this left part here because we have a left-tailed test. And how do I know we have a left-tailed test? I look at my alternative hypotheses. So since this includes a less than, we've got a left-tailed test. Okay, and we're done with this section.
It's 9:45.
Okay, thank you.